Hello everyone, my name is Harrison Williams and today I'll be presenting my Lab 4 report for Physics 2212. So the primary purpose of this experiment was to measure the distance dependence of the magnetic field produced by a small bar magnet. We then compared these experimental measurements to the theoretical predictions provided by the Biot-Savart law, which is modeled in GlowScript for both on-axis and off-axis magnetic fields. To give you a quick preview of my findings, I determined the distance dependence factor n to be negative 5.324 in the magnetic dipole moment, mu to be 2.472 angstroms per meter squared. So before diving into the data, let's look at the physics behind it all. The core principle used here is the Biot-Savart law. This law relates magnetic fields to the currents that create them. For a magnetic dipole like our bar magnets, the magnitude of the magnetic field decreases as the distance r increases. We express this relationship as b bar equals k r to the n. In an ideal scenario, we expect n to be negative 3, representing an inverse cubic relationship. We also use the formula for the magnetic field of a dipole to eventually solve for the magnetic moment mu. So for our setup, the system was a smartphone's internal magnometer, and the surroundings include the Earth's magnetic field and the bar magnet. So the first step to this was to orient the phone to compensate for magnetic north, ensuring the x component of the field started at 0. I then located the exact position of the magnometer sensor within the phone by finding the points where the x and y readings were maximized. I measured the distance required to reach specific magnetic field magnitudes on the axis. Later, I conducted off-axis measurements by moving the phone a distance d both vertically and horizontally to find the net field at a 45-degree angle. So looking at my Excel data, you can see that the logarithmic plot natural log of b of x versus natural log of r, according to the equation natural log of b of x equals natural log of k plus n times the natural log of r. The slope of this line gives us our value for n. So my experimental slope was negative 5.3245 with a y-intercept of negative 11.727. While the expected n value is negative 3, my value of negative 5.3 suggests that the field dropped off much faster than predicted in my specific environment. For the off-axis field, I measured an average d of 0.387 meters, resulting in the net magnitude of 4.33 times 10 to the negative 4 Tesla. So to find the magnetic dipole moment mu, I used the intercept k by setting k equal to mu naught over 4 pi times 2 mu. I then calculated a magnetic moment of 2.472 angstroms per meter squared. I then plugged this mu value into GlowScript to create a function and calculate the magnetic field at any observed location. The model visualizes the field using arrows, orange on axis and cyan for perpendicular. The computational model yielded a 45-degree off-axis field and a 2.402 times 10 to the negative 6 Tesla. When compared to my experimental result of 4.33 times 10 to the negative 4 Tesla, there is a significant disparity. This is likely due to external interference, such as nearby electronics, steel table legs, or slight measurement errors during the manual movement of the smartphone. So, to conclude, let's first address the what-if questions. First, what if I hadn't oriented the experiment to compensate for magnetic north, if the meter was stuck at an intermediate angle? So the Earth's magnetic field would have contributed to the x component of the readings, and this would have led to an inconsistent b of x value and an inaccurate calculation for n and mu. Second, what if I stuck two identical magnets to each other end to end? Due to the principle of superposition, the magnetic field would approximately double in magnitude while the direction would remain the same. All right, thank you for watching.